Good morning. I'm Jeff Brown, Research and Development engineer at the Alabama Department of Transportation. Dr. Fuad had to be called away back to Birmingham, and he was unable to be with us this morning, and he asked me if I would substitute for him. What I like to do is go ahead and introduce all of our speakers up front. I learned this process from a gentleman that's sitting out there yesterday, and it works very well. I'd like to introduce the speakers, each one, and then what I'd like to ask you to do is when the first speaker come up, and when he go into his question mode, if you would come up and get ready to do your presentation. In that order, please. Also, we have a few logistics that I was asked to give you. Lunch will be served in the Georgia Tech Hotel ballroom, and they'll have people around who will direct you to where that is. And the panel meeting will start at noon. Our first speaker is Raul Kalayankar. Second speaker, we have two speakers, will be Margaret Akofie so far, and Janille Smith-Collins, Wang, Sahar, Ghasemi, Vitali, Khaikine, and Mohamed, Salah, Gallow, in that order. Would the first speaker come to the podium, please?
Hello everyone, this is Rahul Kalayankar, and I would like to present my topic is simulation of brain responses to heavy vehicles. As per US Department of Transportation, we have around 11% bridge which are structurally deficient and 13% functionally obsolete. The condition of the bridge, whether they are structurally deficient or obsolete, is determined based on the load rating factor. The determination of load rating factor requires lots of vehicular information like the actual load on the bridge. And there are many methods available to find the load, but I'm just focusing on this advanced system, bridge weighing motion system. Bridge weighing motion system, currently the current bridge weighing motion system works on the principle of Moses algorithm. It uses Moses algorithm. It's an inverse type of analysis where we measure the response, such as strain versus time, on the side, and then we obtain the bending moment through it, and then we obtain the influence line using the vehicle load, and then we can back calculate the live load. This is the equation for the Moses algorithm. There are a few limitations of the current Moses algorithm, such as it uses very simplified formulae, and it's not effective for long span wide bridges, and it doesn't take care of the irregular road surface profile. And vehicle in the Moses algorithm is assumed as you have uniform speed. So in order to address these limitations or the issues with the Moses algorithm, we have proposed moving force identification algorithm. That's an alternative approach for the Moses algorithm to replace the Moses algorithm with MFI. It uses the equation of motion. So basically, it has this algorithm has lots of information coming from the finite element modeling. We measure the structural strain, and we model the FE model, and we obtain the strain from that, and we compare. And once we kind of have the satisfactory result, then we get the M, C, and K matrix from the finite element model. Since we use finite element model in this MFI algorithm, it has a potential of considering the different dynamic forces, such as mass, springs, and dampers, etc. For for this moving, there are different FE models being used for MFI. The challenges involved in the current FE models are those FE models are oversimplified. They don't account really for the truck properties like effect of suspension, damping, etc. Dynamic vehicle to bridge interaction where surface irregularities and gaps, physical parameters and multiple bridges. These are the issues not fully covered in the current FE models. So therefore, our task number 1 is experimental test and FE validation of the bridges. This is the US78 beam bridge that we have selected, and this is the I-459 bridge, and this is the calibration vehicle that I use for the model. Since the time constraint, I'm not going into the finite element how I model this bridges and vehicle. And the validation, basically for the validation of the bridge, I use 2 different approaches. First of all, obtaining the statical deflection using AstroCode, and then obtaining the dynamic deflection for the girders. As you can see, for US78 bridge on the right side, on the left side, we obtain 1.3 millimeter with static and 1.4 millimeter for dynamic. Also for 459, we obtained 2.4, and with the dynamic we obtained around 3. With this validation, the next process is validation of the bridge by one more method, that's getting the natural frequencies. For getting the natural frequencies, we calculated the natural frequencies using the beam equations, and then we measured we extracted the natural frequencies from the measured data, strain versus time curve, and we extracted the natural frequencies using LS-DYNA. There are natural frequencies are matching. Some of them are not matching because there are lots of simplification and lots of assumption we do while calculating the natural frequency. Based on this, this is the first mode shape for US78 and for 459. Moreover, likewise, the vehicle was also validated using 2 different methods, such as the mass distribution and the suspension parameters. In the mass distribution, we modeled the vehicle over the rigid walls, and we obtained the rigid wall forces, and we compared those rigid wall forces with the measured load that we measured on the site. With this mass distribution and the acceptable limit of mass distribution, the second is suspension parameters. For the suspension parameters, the speed bump test was carried out at Florida State University, and in that case, they carried out the experimental work, and they also developed the FE model, and these are the results, experimental and FE analysis. And since there is standard calibration vehicles for most of the states, we have decided to adopt these suspension and damping parameters for this standard truck that we are using for our L-dot truck. It is based on the experimental work, and it is based on the manufacturer's properties provided by the manufacturers. Next, the task number 2 is dynamic vehicle to bridge interaction. Astro LRB code specifies live load based on the impact factor. There are common impact factors for most of the bridges regardless of the nature of the vehicle, and it do not account for the dynamics such as vehicle movement and suspension and damping parameters. Therefore, heavy vehicle to bridge interaction was carried out to observe the response of the bridge under moving heavy vehicle load, and to simulate the FE model and validate the FE response with the experimental test that we carried out. There was few considerations for the simulation, such as contact surface to surface was used, and the transient dynamic analysis was carried out with a truck velocity of 55 miles per hour. And you can see in this is the top one is the US78 bridge, T-beam bridge. The truck is in the left lane. So because truck is in the left lane, we are just considering girder 1 and girder 2. You can see this response. The weighing sensors. Weighing sensors are the sensors we are using to measure the response, to calculate the weight of the truck. And weighing sensors are placed in the mid span. So this is the response of the weighing sensor for girder 1, girder 2. As you can see, they are matching with each other. The final values are very close to each other. For the experimental work, there is not so much vibration involved. That's because they use lots of filtering techniques in it, and that's because of the filtering we kind of get smooth curve. In FE we did not use any filtering. Similarly, for the 459I girder bridge, here the truck is in the eastbound lane over the girder 4 and 5. So this is the response of girder 4 and 5. Now, after getting the responses, and the next step is validating the fat sensor. Fat sensors are the free from axle detection sensors that we use to determine the vehicular characteristics such as velocity, distance between the axles, number of axles, etc. So here we place the two strain gauges, F1, F2 in one lane, and F3 and F4 on other lane. So this is the F1, F2 in the left lane, and F3, F4 in the right lane. This is the experimental response. That the first graph is the experimental response. The second graph is the FE response for the left lane, and similarly for the right. In most of the cases, the peak values represented in the experimental as well as in the FE response represent the axle. So since it is a 5-axle truck, we were able to detect all the 5 peaks for both of them in both cases. And this table summarizes the output. Similar approach was used for for the I-459 with a truck position over there, and responses were obtained using the same technique. Now, dynamic heavy vehicle to bridge interaction was used for the validation of field calibrated data and FE simulation for reliable weight sensor data, and successful. It was used for successfully detect the axles using the fat sensors. But there are a few disadvantages of this dynamic vehicle to bridge interaction. First of all, fat sensors did not show consistent peak values for both bridges, and the total number of elements are very high in both bridges, and that's why we cannot extract the dynamic properties, and therefore we cannot use this FE model in the algorithm. Also, higher simulation time. So based on this, we decided to go for further simplification. So in this case, this is a simplified vehicle to bridge interaction. We have three different stages over here. First is we simplified the bridge, simplified the truck. Second is we use different approaches to simplify the bridge. And third is with the most simplified bridge model that we selected, we look for the effect on the road surface roughness. So first one. Here, this is the truck. We removed the entire body of the truck in order to simplify it. So basically, this is front axle, rear 1, rear 2, trailer 1, trailer 2. For each axle, we have 30. For the entire model, we have 30 mass elements, 20 discrete elements, and 20 for the suspension, and 20 for the damping. This mass element at the bottom provides the stability to the truck, and it provides the contact. The C and K stands for the stiffness and damping for the vehicular tires. This second, the one in the middle is for axle weight. C and K for the suspension and damping of the tire, and the top one is for the axle load, total axle load of the truck. And you can see this table summarizes the response using measure and using FE. And second approach is like, in this case, this is the bridge, which is 3D bridge, but the truck is simplified. And you can see the response of the girder and response of the fat sensors. In girder, the response was in the acceptable limit, and also in the fat sensors, we were able to detect the axle position and axle clearly. Here, the simulation time was reduced to 15 minutes compared to 12 hours that we had. And again, number of elements are 60,000. We cannot use this, so next simulation require more simplification. So here in this case, this is the simplified truck and simplified composite. In this case, we replace the slab and the diaphragm with the shade elements, and the girders are solid. Again, response of girder and the response of fat sensor are there, which are in the acceptable limit again. It did successfully detect the fat response of axis 2. Simulation time reduced to 9 minutes, and number of elements 22,000. We are looking for something which is in the range of 3,000 in order to have a successful implementation of MFI. So dynamic properties cannot be extracted. Second is this third approach is have complete shell beam bridge. Here we have shell elements for the slab and beam elements for the girders. As you can see, the responses are again similar. Here, number of elements 13,000, very high. So what we did is like we use larger shell beam elements here in the fourth approach, and we obtain the responses. Here, simulation time reduced to 1 minute 30 seconds compared to the 12 hours for the full simulation. Number of elements 2,469. This model will be using to extract the stiffness and mass properties. Now, extraction of mass and stiffness matrix. The bridge that I showed you was a US 78 bridge with 1,942 elements. We ran the implicit analysis in order to get the mode shapes and natural frequencies. And also we ran the simulation to obtain the M and K matrices. And based on the M and K matrices, the Rayleigh damping will be used to get the C matrix. Right now the work is in the progress in this case, and we don't have results yet. We are still working on that. Now, moving on third, effect of surface roughness. There are different profiles specified by ASTO, and there is one major roughness roughness was measured by the previous researcher. We use these roughness profiles in our simulation to see the response of this roughness on weighing sensors as well as on the fat sensors. As you can see, when there is no roughness, as you can see the curve is so smooth. But as the roughness increases, you can see in the very poor roughness there are lots of spikes, and this major roughness actually fall in between good roughness and the average roughness. Similar observations were made on the fat sensors. No roughness, clear identification, but as the roughness increases, it almost becomes blurred. So here we cannot, in the poor and very poor roughness profile, we cannot detect the axles. Major roughness again fall in somewhere between good and the average. This, we were able to detect the axles in most of the case when there is a good roughness, but we need to have some filtering technique when there is a poor roughness or very poor roughness. That's the end of my simulation. I would like to thank Florida State University to provide information about modeling and all. And yeah, that's it. Thanks.
Got questions?
Yeah, I think that's a good job you've done. My question is, if I'm a bridge engineer with the DOT, how can I use your results? For instance, I know you're not done, but when you're done, let's say I work with permitting for bridges and stuff like that. How can I use your results?
What we are trying to do is like we're trying to find a domain where, let's say, if a truck passes over the bridge, and if we observe the results like strain data from the bridge, like once we modify this MFI algorithm, then the strain data, and from the strain data, we will be able to find whether the truck is going with the right speed, whether it is in the limit of speed specified or it is above the limit. That's the one thing that we can monitor. Second thing is like if it is falling in the good good speed and everything is fine, then we can see based on the response how the axles are how much weight is coming over the bridge through the axles. What happened most of the time is like truck has the distribution of the mass on the truck, which is not uniform. So you can spot based on the response, you can spot what part, whether it's the front part which is overloaded or rear part which is overloaded. So we are trying to create a domain over there so that once we have the truck going over there, it will directly spot and will say, okay, well this is the issue over there in the truck.
If I can modify my question, in the beginning you mentioned something about load rating, right?
Yeah, load rating.
So as an engineer working for like a DOT, I want to load rate my bridge. I want to see whether you need to post it.
I'm sorry, I forgot.
Whether you need to put a load posting on it or not. there's something about like moment envelopes. Are you familiar with that?
Yeah, yeah.
Okay, so the point is, if you want to relate your results to practical application, how can you make that move?
What we'll be doing is for example, as I said, we have to find first of all whether because the response change with the velocity. So if we have more like fast moving vehicles, then we get different responses. If we have a slow vehicle, we get different responses. So what we're trying to do, like we're trying to fix the limit where we should monitor this BVM data. And if we can fix that limit, like the upper and lower, and if we know that like let's say 40 miles to 70 miles, the truck is running in that range, and if we are getting kind of loading data, like the stress strain curve for the weighing sensors, then that is where the truck or the observation should be made. If the truck is going faster, then we have to say, let's say, disregard this truck. We cannot use these results because the speed is too fast or too slow. So that's what we are trying to create the domain to see this is the speed limit and this is the position, and this is if the position is in the lateral direction, then how it is affecting the bridge and how it is distributing the load over the bridge. And if that domain is once set, then we'll be able to find whether the position of the truck and the speed and the weight of the axle into the axle.
All right, thank you.
Questions? We may have time for one more.
Does the wind vibration take into account this modeling?
I'm sorry?
The wind vibration,
Uh-huh.
you take it into account as modeling when the truck go over the bridge?
The wind vibration, right?
Yes.
Well, we didn't get the chance to look into the wind vibration, but I think when the truck has like lateral wind, it is definitely going to affect the vibration.
You want to thank our presenter? If you have additional questions, you may want to call me out in the session.
Can you hear me? Because I don't have anywhere to clip the microphone, so I'm just going to present without it. Hopefully you can hear me. My name is Janille Smith-Colin. I am a graduate research student here at Georgia Tech, and I'm in the infrastructure research group. And today I'll be talking to you about the prototype evidence-based database for transportation asset management. So before I begin, I just want to point out that this has been a collaborative effort within our research group, and we have two documents that are available. The first is the report that we submitted to Georgia Department of Transportation earlier this month, and it really talks about the process of developing this database that I'm going to present. And the second was a collaborative effort between myself, Jamie Fisher, Margaret Sola, and Dr. Amakuji, and that's a paper that we have forthcoming in TRR. So just to go on, for the agenda, I'm going to talk to you about some of the fundamental concepts of this that surround this project and the background, then discuss with you the research objectives and the methodology, talk to you about our primary data collection effort, which was a TAM evidence exchange as we called it, and then present to you the database as well as the documentation framework that supports the database. So the fundamental concepts. So what is TAM, or Transportation Asset Management? It's a strategic process for maintaining and operating assets. And it looks at the entire life cycle of the asset, and it is kind of quantified based on the maturity scale as defined by AASHTO. And per MAC 21, there's a lot of discussion these days about agencies developing their transportation asset management plans and looking at ways to better improve their decision-making around the transportation asset management process. So another idea that we looked at in this project is called the evidence-based approach, and it originated in healthcare and medicine, and it looks at using evidence of the past to inform practices in the future. And kind of the key elements of the evidence-based approach is that they want to use the best available evidence, they want it to be accumulated and documented over time, they have systematic methods for testing it, and it has to involve practitioner input. So when we looked at the evidence-based approach, just so you have an idea, some of the applications of the evidence-based approach are wide scale at this point. We have seen it in healthcare, we've seen it in education, business management, and social policy. And on this slide, you'll see these are some of the areas in which and how they're defined. In healthcare design of buildings, they use evidence-based design. In education, they'll look at evidence-based decision-making to inform better outcomes for their students. And in business, for example, they use evidence-based management. And so we saw the use of that idea in organizational management as well as business practices. We took a look at transportation just to see what's been done in transportation as far as the evidence-based approach. And we looked in the Transportation Research Board database, and we saw studies dating back as far as 1999 that actually referenced the idea of an evidence-based approach. We found about 50 studies. However, we found that on the most part, there weren't systematic methods defined or rigorous testing defined within the study that was published or available in TRID. That's not to say that they did not have those methodologies, but we found it kind of difficult to discern how they were linking their interventions and their outcomes. And that's kind of a key requirement of the evidence-based approach. We did see that it was mostly used in traffic safety and intervention prevention, and that makes sense because in those fields, there is a clear outcome, and that is that we want to reduce fatalities, and in some cases have zero fatalities. So it is clear, or there's the ability to see what the outcome is when you implement an intervention. We saw it used in other areas as are listed on this slide. We found the one asset management study, which was actually our own as it was being cited in TRID. So we definitely felt that there was an area here and a need to apply the evidence-based approach to transportation asset management. So what are the research objectives for this project? It was to develop a framework for evidence-based transportation asset management, as we called it, or EBTAM. We wanted to allow for the use of best available evidence in transportation asset management and decision-making as we move forward. And we wanted a way to link the idea of evidence to the TAM maturity scale that's already existent and being used by agencies in transportation asset management. And kind of the final ultimate goal was to develop a database that can be used to accumulate evidence about TAM decision-making to allow it to be used to inform practices in the future based on what is happening today. And so the equation at the bottom is just kind of a simplification of that. We wanted to look at evidence-based decision-making, apply it to transportation asset management, and come up with a framework for evidence-based transportation asset management that can be used moving forward. So our methodology, we looked at the evidence-based approach, and it kind of has a systematic methodology that is used to conduct their studies. It's similar to that which is used in several fields, but it does exist. So we did a literature review, as I discussed, of evidence-based approaches in other fields. We looked at what was being done in transportation, and then we went ahead and we had our data collection effort. And for us, that involved the TAM evidence exchange, which was where we allowed practitioners to provide input to our study, and we actually hosted that as a series of 3 webinars that consisted of a presentation that was provided to them, and then a roundtable discussion where they could provide feedback on the project and where they thought the project should go moving forward. We then did a case study analysis of asset management case studies and synthesized that information, developed a documentation framework where we could systematically document our findings, and then began the development of the prototype database. So the TAM evidence exchange, as I discussed, was a webinar series, and we had about 20 or so practitioners from 10 or so agencies, DOTs, as well as consultants participate in the project. We had findings from this effort, and we organized those findings based on themes, and we kind of documented key observations that the practitioners provided us about the effort itself. So we had system integration as the first theme, and one of the things that came up, of course, was that as a TAM asset management professional, there are trade-offs that need to be made. And there was definitely, concern expressed about the fact that these trade-offs had to be made, and that sometimes there wasn't great information supporting the need to make those decisions. Data collection. Practitioners are less inclined to be told that they need to collect more data. What we found was that they really wanted to know how they could use the data that they had now, how they could best make better decisions moving forward. and how they could limit the ability, the need to collect more because of limited resources. Evidence quality. So what we found was that there were some issues with documentation. There are interventions that do happen in practice that sometimes are not necessarily documented. They're kept with the practitioner, and there is a fear that if that one practitioner was to leave, that there was a lack of knowledge continuity moving forward. So we found that documentation would be key, and this is actually a theme that is recurring within the evidence-based approach. That documentation is important, and that for improvement in the future, you need to know what interventions you did now and link that to the outcomes. So the other themes were knowledge transfer, risk management, and investment. As far as knowledge transfer, there was some discussion from the practitioners about the feedback loop, that when they do have interventions, sometimes there isn't an opportunity to go back and look to see what worked and what didn't, and that there was an interest in improving that feedback loop and having a better methodology for improving it. Risk management, whether or not it was acceptable to have a documented level of risk. For asset management, is it okay that things are going to fail, and at what level is that acceptable? And of course, this project doesn't speak to that specifically, but within our research group, we do have people that look at risk management and when that's acceptable and when it's not. And the last topic that kind of came forward was investment trade-offs. As they make these decisions about trade-off analysis, practitioners did indicate that they would love to have additional information about good methodologies for that kind of analysis and making those decisions moving forward. So, adding to the theme of documentation, we developed a framework called PICMO to assist with the documentation of interventions and linking those interventions to outcomes within transportation asset management. Now, PICMO, Problem, Intervention, Context, Mechanisms, and Outcomes, is actually a hybrid based on a literature review that we did. We found that PICO is prominently used in healthcare, and that's Problem, Intervention, Context, and Outcomes. And we found that CIMO is prominently used more in the social sciences, which is Context, Intervention, Mechanisms, Outcomes. So we combine those because we believe that in transportation asset management, the context of your decision is so important because every agency is different. And then of course, documenting those mechanisms that you use to identify your evidence is equally as important. So the hybrid framework that we use to investigate outcomes in asset management for this project was PICMO. So what are some of the assessment questions that we asked? We would ask an agency to, when they implement something, go back through that feedback process to see what the outcomes were, to ask themselves, what was the problem that you solved? You know, what interventions did you use to address the problem? What was the context or the relationships or institutional settings that may have affected these outcomes? What mechanisms did you use to evaluate your outcome? How do you know that your project worked? And what was the outcome? And some of these things may seem intuitive, but oftentimes practitioners need to take a moment to stop, like everybody else, and say, hey, what did I do and what was the outcome? So just as an example application, we had a project come to us where the problem was that the agency really did not know what their TAM capabilities were. So they decided that they were going to, as an intervention, inventory all of their roadway segments to identify their needs and their gaps. And for them, the context that led to that was just a strategic need to understand what was happening within their program and the fact that they were being faced with limited funding. And they wanted to take a look at their asset management program to see how it could be improved. They used a 2-year pilot study to evaluate these outcomes and to make the connections between their interventions. And at the end, they took a stop and they had the outcome of restructuring their asset management program. They actually found out that they had kind of lofty ideas about their asset management program, that they were more at the inception stages, and so they restructured it to make data collection their priority in this case, and then to monitor that over the 6 years. And they actually saw improvement in the way their asset management program was implemented over time. So the database was kind of the primary outcome of this project. And there is a movement within the transportation asset management arena, and it's being led by NCHRP to develop asset management knowledge. And they're actually working on a knowledge database. So this, we believe, was a good input to that effort. So our database is really used primarily to document your interventions and your outcomes based on the PICMO framework. And it says that the purpose is to document the planning and help planning agencies to implement their TAM asset management program over time by accumulating evidence of any high performance outcomes that they may have had, and potentially any less successful outcomes that they may have had as well. So the database allows you to enter a new entry with a brief-in entry portion of it, and it allows you to view, and then of course allows you to search. So it's intended to kind of be a peer exchange framework for practitioners. So the first thing that you would have to do as an agency if you went in is that you would enter your contact information. And this is because the database itself is intended to be searchable by different fields, one of them being who entered the information, what agency they represented. So for example, you knew that agency X had a great success, you could come in here and search the database by that person's name or that person's agency. So we have that contact information, so any practitioner can go and exchange information. The key portion of the database is the record entry portion. And so the database asks the practitioner to respond to several questions about the TAM information that they had. And these questions are based on the PICMO framework. So it does ask you, for example, what was your problem? What were the interventions that you used to solve this problem? What was the context in which you explored this intervention? And then what were the outcomes? And so of course the idea here, based on the evidence-based approach, is to have this information clearly documented and to hopefully over time accumulate similar interventions within one space that can be searched and used by practitioners. So the main database creates a record ID, of course, an agency type, a name is available, and the person's information is listed. And then it provides you the information that's entered in a condensed way. So the idea would be to have multiple entries of different ID records that have been entered by agencies. And so they would have listed there what was that problem. We also went ahead for the database purpose and added the asset column so that you would be able to search the database potentially by asset type, and then you could get your other information about outcomes and motivation. So one of the issues that is a concern within an evidence-based approach is what is the quality of the information that's being collected? And of course, this can be a subjective item. It's not necessarily quantifiable through numbers, but we have made an attempt in this database to do so. So to evaluate evidence quality, we came up with 3 fields that are within the database. The first is level of completeness. And that really is just an indication of how complete the record is within the database. So that means, was the agency able to answer our PICMO questions within the database? And to what extent did they do so? Confidence level. The database asks the reporting agency, how confident are you that the intervention that you put into place led to this particular outcome? Now we also recognize that there are many interventions that may lead to outcomes, and there's not necessarily a one-to-one attribution, and that of course is a separate discussion. But we wanted to be able to capture here what the agency felt was the true outcome, and were they confident in that? And the last thing that we asked is, what value do you think that this intervention added to your TAM asset management program, and what value did the outcome add? And within the database, we actually have fields that demonstrate that. As you can see here, confidence level and value added are rated on a high, low, medium scale. And so we would ask the agency to go in and indicate what their responses to those questions. We've allowed comments to maybe have them indicate, why they feel the way they do, and what were the indicators that led to this response. And then from level of completeness, it's really just a percentage bar that is measured based on the completeness of the record and whether or not the agency answered those questions. So for another agency viewing this database, they can kind of get a sense of what agency X felt was the outcome, and if they do have questions, they can go to that agency and ask them. So one of the main objectives of this project, of course, was to link TAM maturity to evidence. Now, the transportation asset management per AASHTO is defined on a maturity scale that starts with initial being the first level and best practice number 5 being the last level. And it's assumed that at every increasing level of maturity that there's more evidence being used in your TAM maturity program, in your TAM program. In fact, TAM has actually been defined by some as a use of best case evidence to support transportation asset management. So we took a look at what mechanisms we would expect to be used at differing levels of maturity. So we would think that an agency that is at their initial levels of TAM maturity would use, for example, a single case study to analyze their work, and really just practitioner and gut feeling to analyze their work. And we would think that too, and as you move from being least mature to most mature, the least mature position would have a high level of bias because of course it may just be one practitioner or one study that's informing your decision making. And you would have reduced bias when you get to the best practice level. So we've here provided some input to agencies on what kind of mechanisms you should be using as you become more and more mature. And of course, we also realize that it's cumulative. Someone who is very mature may very well use practitioner input and use that gut feeling to make their decisions. But we would think that they are using higher and higher quality evidence to inform their decision making, so that when you get to that best practice level, you have the highest quality of evidence that's informing your decisions. For example, through a methodology as a business case analysis, where there's quite a bit of data collected and retrospective looking back to see what worked in the past and how you should move forward in the future. So for future work, we hope to deploy this database on a web-based, user-friendly platform. Right now it's in Excel, and it was coded through Visual Basic macros, but maybe there is a better way to put this out for use by practitioners. We want to increase search functionality. We would hope that we could search by agency type as well as asset, as well as specific problems. And as we accumulate evidence over time, that we could develop enough information to make that a searchable entity. We want to continue to work on the hierarchy that I just presented, that like links evidence to TAM. We want to continue to flush that out. In other fields, in healthcare, for example, there is actually an established hierarchy that practitioners have agreed on as far as what is their most highest level of quality generation. So for healthcare, for example, the practitioner input is actually at the lowest level. And they go as high as having randomized controlled studies. And so we want to continue to work on that information moving forward. We want to continue to define the idea of quality evidence, whether it be by level of completeness or value added, and document more studies using the PICMO framework so that ultimately we can continue to populate the EBTAM database and make it available for use by practitioners. And so we just want to thank the Georgia Department of Transportation and the UTC for their funding in the work of this project, and I'll take any questions now. Thank you.
We have time for maybe one question. Thank you so much. Sorry.
Tell us about the interaction between EB and we have not only one database for one asset, but multiple assets. How the interaction we study.
Between them?
Yeah.
So are you saying how would we include that within the database?
Oh, well, study them inclusively together.
Well, hopefully moving forward, that's something that we could do. We could continue to work on this database project, and we could look at other databases that are available so that we can continue to look at them inclusively.
Thank you so much.
Beginning slide, just to be sure, the email bombarding from Audrey did have some effect. So good morning, everyone. My name is Wang. I'm associate professor in civil environmental engineering at Georgia Tech. I'm here to present our research sponsored by our University Transportation Center. And it's a collaborative research between my research group and Dr. Nassim Ali's group at UAB, and Dr. Larry Jacobs and the Jin Kim's group at Georgia Tech. I want to first thank the student co-authors, Xinjun Dao and Shuo, for their hard work. And this is a research project that develops a next generation wireless sensing system for our nation's infrastructure for transportation safety. So I'll start with a motivation background and then introduce the development in our sensing platform, the latest generation. And I'll talk about two validation tests. First one is a large-scale wireless acceleration test, and second one is a fatigue specimen test, cracking a aluminum specimen using the sensors to detect the crack development. And I'll also introduce a little bit, although you have seen quite a bit in our first presentation from our collaborators group at Birmingham, a little of their latest results in wave motion analysis. So, as civil engineers, most of us have seen this latest ASE rating on the America's infrastructure. So the deterioration of our infrastructure is adding daily cost to our everyday lives, and failure of critical infrastructure may even endanger public safety. And with the current budget situation, taking bridges and highways as example, 91 billion is the current spending, and we want to improve all those C and D grades up to a B condition. There's just not enough money to do them all. So there's a need for bridge inspection so that we can use those limited resources on the most dangerous structures. And currently, a regular bridge is inspected once every 2 years. So that is a relatively long time span. Many things can happen in the 2 years. And current practice is visual inspection, which can be subjective, and it's hard to see what's happening inside the structure. You can only see the surface. So there's a need for structural sensing systems that can autonomously monitor the safety conditions of the structures. So you put sensors on the structure, monitoring the condition, and if anything happens, hopefully the sensor will capture that. So traditionally, sensing systems on civil structures are cable-based systems. So you lay long cables on for example, a bridge to power the sensors and also to get data from sensors. Apparently, cables take a long time to install, and cables are costly. And for large structures, you need kilometers of cables and almost a year to do the installation. So if we replace those cable sensors with wireless sensors, definitely we're eliminating all the time and cost associated with cables. And another advancement enabled by electronic technologies that we're not just doing wireless sensors, but also we call them smart wireless sensors. So each wireless sensing node has a little computer chip inside, computer processor, so that not only those sensing nodes can collect the data, but also they can chat with each other, and they can use the computer chip to do processing, to do computing, and to even make certain intelligent decision with the data that they collected. So that is why those sensors are called smart wireless sensors. Almost 2 decades ago, people have started working on wireless sensors for structures, and we have really come a long way in the last 2 decades. And even myself, I've been in the business for more than 10 years. That was the wireless sensing prototype I developed when I was a PhD student 10 years ago. So as we can see, the size of the sensing devices are shrinking, becoming smaller and smaller, and the computing power and wireless communication capabilities are getting stronger and stronger. So what I'm presenting here today is really building upon our past 10 years of experience, a latest generation wireless sensing platform that we have recently developed. So the background for our project is to first use wireless sensors, not just for monitoring, but also for ultrasonic non-destructive evaluation, ultrasonic sensing on the structure. So the way it works is that you have an ultrasonic transmitter and ultrasonic receiver, and that's a blow-up of the picture. If a crack happens, so the transmitter sends a megahertz or kilohertz excitation solid vibration waves into the structural component, into the solid, either steel or concrete. Then there's high frequency vibration happening in this local area. Then I receive the signal. If there's some crack happening, my received signal would show some difference. So we are developing our latest generation wireless device so that it's capable of doing not just regular string or acceleration measurements, but also capable of this high frequency megahertz ultrasonic excitation and sampling. A second motivation is working with our collaborators at Birmingham to develop this motion platform. We use wireless sensors to measure the bridge dynamic response when a heavy truck drives by. And from the response data, we try to derive the truck weight so that if the truck is overloaded, is overweight, potentially we could help the cops to catch them. And that's a photo from our partners at Birmingham. That's a traditional cable-based wind motion sensor, wind motion system. And looking at this spider web, there's definitely a need to go wireless. So an overall picture of our project works like this. We have those wireless sensing units on the bridge. They monitor bridge dynamic response, stress, strain, accelerations, ultrasonic NDE, etc. And we have a local gateway that aggregates all this data from the bridge. Then through cell phone network, the data can be pushed into a computer in the office. And we've been working with Dr. Gonsalves group, and we've been helping significantly with their expertise in this cell phone network data transmission. So we are very excited to get this entire system working and hopefully to give GDOT a demo in the second week of April. On the wireless sensing unit side, we have been collaborating with a research group in the University of Michigan, another group at Michigan Tech, to develop this new generation wireless sensing system. We call that Martlet. So the core components of this wireless sensing unit are those three blocks on top. There's sensor signal digitalization, there's a computational core for executing computing, there's a wireless communication module for talking to other wireless nodes or talking to a central server. And the wireless unit can take sensor data from wind motion sensors, like those free of axle sensors or those wind sensors that you saw in the first presentation. And also, it's capable of exciting the ultrasonic transducer so that the solid vibration waves that goes into your structural component and is able to get response from another transducer. And this unit was just, this latest platform was just rolled out 2 weeks ago at a conference in San Diego. Again, it's a collaborative effort between 3 university labs. And we call this Martlet. By the way, Martlet is the name of a small and fast bird, so that's as far as I know. The student who worked on this project gave this name. I did not know this English word before. So the unit uses a chipcom Zigbee compatible radio, supports a data rate of 250 kbps. And we specialize radio so that the transmission goes up to 500 meters in line of sight. So it's a good range to cover a typical highway bridge. And wireless unit has an 18 megahertz computational core. It has a floating point unit embedded in the computational core so that it is very fast in number crunching. You have your algorithms. For example, for a transform to get the frequency information on the data, it's just a split second, it can do the computing for you. And it supports a very light radio frequency stack, and that means the radio frequency protocol so that the communication is fast and is real time. And the program of this microprocessor is just standard C language. So every engineering student will be capable of doing this. And supports modular. This is the motherboard. We have different modules, which you will see on the next slide, for different applications. And the programming of this microprocessor is just through this USB port, you connect with your computer, get all the graphical user interface for doing the coding, debugging. So it's very convenient to program. And those are the daughter boards, and we call those motors of wings. So those are depending on different applications you have, you stack those daughter boards onto the motherboard. There's battery charger, there's prototyping board to get the tensile pins out from microprocessor, so you can use oscilloscope to touch the pin to watch the signal exactly. A real-time clock has the accuracy of 1 minute per year. It's got a smart filter, digital analog converter, and if you want to use with a acceleration sensor, you can use this board to connect with your accelerometer. It's got the temperature sensor on top of it too. And the device has also been used for hydraulic applications, for pumps and valves, and even motor control. And this is for carbon dioxide monitoring. So we developed this baseboard really exploring all possible applications. And the last two boards, string gauge board and ultrasonic pitch catching, are the two boards that are mainly used on this UTC/GDOT project. As I said, at this motherboard at the bottom, you can plug on different daughter boards on top. And top I'm showing here the general analog to digital conversion or digital analog conversion board. It supports on-the-fly programmable gain and cutoff frequencies. So that is for amplifying your sensor signal and filter out the sensor noise automatically. And the string gauge board can support a 120 ohm or 350 ohm string gauge people typically use, and supports a wide string range. And our calibration shows very good accuracy. The noise floor is only 1 or 2 micro strings. Ultrasonic board is capable of generating up to 500 kilohertz excitation. Those are real high frequency vibration in a local area of the structural component for crack detection. And we can sample data at 3 megahertz. That means every 1 second is 3 million data samples. So that's the kind of speed you need for ultrasonic application. So just 2 weeks ago, when I was making the presentation at San Diego, we did a large-scale validation test of this water sensing system. It's really an SF project led by Dr. DeRoche for seismic retrofit of reinforced concrete building structures. So we constructed 4 identical 2-story, 2-bay frame structures in the yard outside the GT Structures Lab. You can see in this picture, this main piece you see is a collapse prevention frame. So that's not one of the 4. The one right next to it, that's the first one, second one, third, fourth. And the other side is another collapse prevention frame. So 4 identical frames. 2 weeks ago, we tested the first frame. You can see this piece of a large chunk of metal is a large shaker shaped here from UCLA. That's mounted on the roof, and it shakes the structure till the structure is damaged. We had 2 types of water sensing systems. So Norada is the prior generation water sensing system, and MarkLab is this latest generation system because it's a new development. We have not made large quantities yet. So overall, we have 66 wireless observation channels on this structure. You can see all this dense instrumentation on this one single 2-story, 2-bay frame structure, which is giving us a large quantity of data which has the potential to generate a 10 PhD thesis, we believe. These are some example data from the structure. This is from we call first elevated slab. That's from the ceiling of the first floor, and that's just a roof. That's the second elevated slab. And right-hand side shows a zooming of the signal. You can see very clean vibration signal. So horizontal axis is in seconds, and vertical axis is in gravity acceleration g. You can see the amplitude of the vibration. And the second validation test I'm presenting here today is a fatigue test. So we have a piece of